Can everyone hear me okay? All right. So how many people are continuing from the first half versus just arriving? And, all right, I think I said both. How many people are just arriving? Okay, so just maybe, right, where we recapped is we covered sort of a crash course of just sort of overview of more or less what's happened in deep learning and the basic structure and training paradigm of building large neural networks and backpropagating gradients. And we sort of saw in code the realization of how you'd accomplish these things with MXNet. So we saw the basic data structures, how you take gradients, how you use predefined layers through the abstractions provided by MXNet Glueon. And we kind of ended up with Alex going through sort of deep neural networks, convolutional neural networks specifically, that are used for computer vision, and showing how you wind up often sort of now defining networks programmatically with repeating blocks, where you can wind up having many, many layers of computation happening between your inputs and your outputs. So one of the elements that's common to use in the recurring repeating blocks of neural network layers is called batch normalization. And this is basically motivated by the fact that you wind up with these very, very, very large structures where you insert your data at the beginning, you compute upon them many, many times, and then you calculate your loss at the very top. And you start off with a completely random initialization. And one thing that can happen is that over the course of training, if you just look at a single layer network, right? If you just had your linear model, your input distribution stays the same, and you're just trying to learn the right parameters to map from your input distribution to what the output should be. With these very, very deep neural networks, actually the input is constantly changing, right? The input to each layer is the output of the previous layer. So you wind up with a situation where in the beginning of training, you might have initialized with very small weights, and potentially the activations come in, have some distribution where the values tend to be very small. And then over the course of training, this might shift dramatically. It might no longer look Gaussian. The scale, the magnitudes of the activations might be 10 times or 100 times what it was initially. And so this motivated some people who were concerned about, like, is there a way to address what you think of as sort of this covariate shift, that actually your inputs are drifting over time. And so batch normalization is kind of a simple, clever idea that ends up drastically improving the speed of convergence of neural networks. And essentially what we do is we basically just say, I'm going to keep track of some sort of summary statistics of the activations that go into each layer. So basically we're saying we're going to compute a mean and we're going to compute a variance. And these are of the inputs to every single layer. And then we're going to normalize that by them. So we're going to subtract the mean from the inputs, and we're going to divide by the standard deviation. Basically what this does is it makes the gradient calculations nice. It keeps the scale of the gradients kind of similar. And so it makes training kind of less erratic, and it's sort of a standard thing that's sort of used sort of throughout computer vision right now. So if you're interested in looking at sort of our realizations of whether it's AlexNet or VGG, which we had described, or SqueezeNet, which is sort of a parsimonious model that's meant to use sort of few parameters and have a low footprint. So it's quite popular for running neural networks on mobile devices. Inception, which is a big scary network that we had looked at before, or residual networks, which kind of combine batch normalization with another nice trick. These are sort of standard models that are now, or at one point have been, sort of the state of the art for image recognition, and they're all available in our model zoo through gluon.modelzoo.vision. And so one nice thing is that also for any model that you might find that's maybe available in PyTorch but not available in Gluon, that import is kind of trivial. Because we sort of both have the imperative interface, so you can do more or less a line-for-line conversion, and it'll work. Alex, you already covered a bit of hybridization, so yeah. And I think we already talked quite a bit about SGD momentum. So I guess we're up to now. Let's maybe start with the, yes, and did we get to the dropout slides?
No.
Okay, cool, I was explaining someone else that. Okay, so I also showed you maybe a working neural network, some examples of like a Gluon network that had dropout defined. What dropout actually does, just to explain it for those of you seeing it for the first time, it's basically what we're worried about, when we're training neural networks, we're often operating in a space where we have a lot of parameters. We might even have more parameters than data points. This is a setting in which we're often worried about overfitting, right? We don't want a model that sort of just trivially fits our training set without recovering sort of the actual pattern, the meaningful pattern that's going to carry over to our sort of previously unseen data. Dropout is an effective technique that basically says, well, sort of motivated by an idea of, well, what is overfitting? Overfitting means you memorize your inputs. What if the network never actually sees the same inputs twice? So the way that you calculate, the way that you incorporate dropout into a neural network is essentially on every single time you make a pass through the network, you're going to, with some probability, but let's just say 1/2 for didactic purposes, you're going to take half of the nodes in every layer of the neural network and flush their values to 0. So you're going to calculate hidden layer 1, set half the values to 0. Now you're going to calculate hidden layer 2, set half the values to 0. And you're not going to set any, you're not going to determine this set deterministically. You're actually going to flip a coin every single time. So you're going to get a random mask that you're going to, essentially you can even just like multiply by a Bernoulli mask. So essentially, now every single time during training that you calculate layer 2, you're seeing inputs that you've never seen before. Now, you're seeing an example that you've seen before, and these inputs are calculated on an example that you've seen before, but it can't rely on the same exact feature detectors being on. So if you think of each layer as a feature extractor, you're getting a different subset of the features on every single pass through the neural net. And this makes it much more difficult, say, to just memorize what was your input. So the way dropout then works is, well, when we're actually doing predictions after we've learned a model that we hope hasn't overfit, we actually want to use all of our parameters, right? We don't want to throw away half the model. So what you can think of is that during training time, we're flushing half of our values to 0. And then at inference time, what we're doing is we're going to average those models. And so the average of the models, right, for each node, half of the time it's on, half of the time it's off. So basically, we're just going to use all of the nodes, but we're going to set their values to 1/2. So it's essentially averaging across all the different dropout masks. So this is it's a really nice idea because it's really simple. We can actually show you the notebook where we implement it in even from scratch, and you can really drop out in about 3 lines. And it's a sort of idea that what's nice about it is, one, it's so simple, anyone can understand it, even if maybe not know theoretically why it works. And also, it tends to work on almost every problem. So this is something that, with a slight modification, you can add to recurrent neural networks. You can do it when you're working with multi-layer perceptrons. You can do it when you're working with convolutional neural networks, and it tends to be effective. One kind of like pro tip is that people tend to, when you have a convolutional neural network, set a lower dropout rate for the convolutional layers than for the fully connected layers. The intuition here is that even though you have a lot of activations in the convolutional layers, you actually don't have many parameters because you're reusing the same parameters at every single patch in the image. So you're not as worried about overfitting with those sometimes as you might be with, say, fully connected layers. In, say, VGG or AlexNet, for example, the vast majority of the weights are actually in the fully connected layers, not in the convolutional part of the network. Another trick that's related to dropout is drop connect. This is basically the same exact idea, only instead of being applied to the activations, it's applied to the weights. So every single time I calculate a layer, I'm going to zero out half the weights before I calculate that layer. And apparently it gives slightly better performance. In fact, actually, there's a cool paper, if you guys are into recurrent neural networks, that shows that doing drop connect on RNNs and LSTMs, but using the same mask at every single time step gives now state-of-the-art results for perplexity So if you're interested in like language modeling or that kind of thing, it's a pretty effective technique. Basically, you get the idea. Draw a new mask for every single step. Calculate the output from the input. Do backprop. The backprop, basically, the gradient only flows through the nodes that were on that particular path. It doesn't flow through the nodes that were off. But across many, many different draws and many different dropout masks, every node's going to be on half the time. So all of your parameters end up getting used and get updated. And then, given that dropout mask, just thinking of it as some sort of input to the network, then it's clear that the whole thing is still fully differentiable. This picture just gives you kind of a nice little visualization of what's happening. The middle figure is dropout. We basically cut off the value from this node that doesn't pass into the next layer. Drop connect is kind of similar, but it's just for zeroing out the weights. And the figure is kind of self-explanatory, so I won't do too much into it. So, great. You can see I put a little disclaimer here. It's a very rough draft, but it's not too bad. Is that better? Yeah. Right, so this is a little figure I drew up. I think it just makes it quite clear what's happening. So you can think of it, right, as just on every single forward pass, you have a different architecture. But that architecture is sort of the architecture made out of a subset of the nodes from the original one. A question in the back?
So at prediction time, do you sample multiple dropout masks and average them, or do you just sample one dropout?
Well, so at every single layer, if you were to go over all, so say you have n nodes at layer 1. Now, if I were to go over every single dropout mask, and because they're drawn independently, the coins flipped independently, they're all equally likely, right? If I were to go and average across every single dropout mask, what happens at that layer? It's basically the same as if I just use all the nodes but divided their value by 2. It's a little more general than that, right? You could set any dropout rate. So that dropout rate could be I only drop out 30%, but then I'm going to scale up by, 3. Or, I could use 33% and scale up by 3. I can use half and scale up by 2, or scale down by 2. But you get the idea. So, I think it's probably easiest to just see it in code. So here, this is all that dropout is doing, right? And most of these lines are just to guard against a divide by 0, which will never happen unless you actually set the dropout rate to 1, which doesn't make any sense because then you're not looking at your input. So, right, the probability that a node is on is just 1 minus the dropout rate. The mask is we could basically just say, I'm going to take a uniform number between 0 and 1, and if it's less than the keep probability, then I'm going to keep it. So if the keep probability is 1, then I keep everything. If the keep probability is 0.5, I keep half the values. And now I have a binary mask. Right? So this is all I'm saying. Just checking if it's greater than, the keep probability is greater than 0. I just don't want to divide by 0. That's all that's going on here. And so I set a scale now, right? The scale is just 1 divided by the keep probability. So if the keep probability is 0.5. So scaling down at prediction time is equivalent to scaling up at training time. So you could define the model either way. In this particular example, I defined it so that we're essentially scaling up during training time, right? So at the end, I could just use the weights, and I don't even have to know that dropout was ever used when it was training. So it's kind of a little bit more elegant in that way. The inference network doesn't even have to have the dropout layer defined. So to make it a no-op in that case. So here's an example. Let's just take a network where basically the values of the entries are sequential, so it's easy to visualize, right? So if we set the dropout rate to 0, then it's basically nothing has happened. We just get back the original values. So you could define a network that basically always uses dropout and takes a parameter that you pass in during training if you want really fine-grained control. So this is sometimes the case, especially if you're experimenting or trying to get just some practitioner's intuition, see what happens if I screw around with it. And you could just make it so this is a parameter that you pass in at prediction time. Now if I set the value to 0.5, you're going to see that some of the values are going to get zeroed out, roughly half of them. Right? And if I set it to 1, then I get the sort of, I basically gated it off, no activation gets through. And otherwise, the training loop looks exactly the same as what we've become accustomed to. We're just going to grab some data, put it on the GPU, grab some labels, put them on the GPU, say that we're going to record. In this case, because I defined my net myself from scratch, I basically made it a parameter that I pass in at train time. So when I call net on the data, I tell it what the dropout rate is. Make a gradient update, and it's quite easy. Now, to do it in Glueon, this actually exposes some new features in Glueon that we recently added. So an important thing to take away from this is that dropout and batch normalization too are two. Remember, batch normalization, you divide by summary statistics, the mean and the variance of each of the features computed on the batch. But at training time, you might not have a batch. You might just have a single image. So what you do with batch normalization at prediction time is you actually will just have a stored moving average of what were the variances and what were the means for each layer. So basically, the important thing to take away from there is that you have a layer now, which whether or not you could remember how it's functionally used, even if you don't remember all the details of it, and you could use it in a Glueon. The main thing that you need to take away and remember is that this is a layer that behaves differently depending on whether you're training or whether you're predicting. Dropout similarly behaves differently depending on whether you're training or whether you're making predictions. So what we need is when we have these layers that have different behavior, where the behavior is contingent upon whether we're in train mode or predict mode, we need some way to explicitly tell Glueon, like, yo, I want to do this in train mode, or no, I want the behavior from predict mode. Otherwise, it's sort of trivial to use dropout in Glueon because it's predefined for us. So all we have to do is add these layers, drop out here and drop out here. There's nothing else that's new. But once we actually want to record, basically, so you remember we actually place our calculation in the network inside a autograd.record block, right? Now, additionally, we have we call that a scope, right? Basically, anything that inside that scope, MXNet knows record is on. We need to record where everything comes from, so we could take a gradient later. Now we're just basically introducing two new scopes. So before you learned about record, everything inside record gets recorded. Now we have predict. So predict mode, everything that happens inside there, the functions who have sort of mode contingent behavior behave the way that they should at prediction time if you put it in a predict mode block. Similarly, we have train mode, right? And train mode should behave the way you expect it to when you're training. And so in the case of dropout, that means you should actually drop out half the values in the case of predict mode. So in this case, if you have this code right here, you actually have to set the dropout rate, which might default to 0 to something like 0.5 or 0.8, and you'll see that these values will come out. And instead of but if you do the same thing over here, the values will be unchanged because you're in predict mode. So corresponding to these scopes of train mode and predict mode is you might at some point want to write your own layer. You might want to actually be able to programmatically determine, am I in the is training state or am I not? And you could do that just by actually accessing autograd.isTraining. So if you're inside a predict block and you type autograd.isTraining, it's going to return the value false. If you're inside train mode, then you're going to get the value true. So the crucial thing here is now we have a common use case that is like the dominant use case, right? Which is I am training a model and I want to record gradients and I want to be in train mode. Or I am making predictions and I don't want to record gradients and I don't want to be in train mode. Moreover, we have some people who might be using models who don't even know what train mode is. They just get the model to use sort of like it's a pre-trained model and now you pass it to your developer. And they might not even know about recording. So it's really important that the default mode be basically to predict and not to train. Does that make sense? But at the same time, you don't want to have to nest two scopes every single time you want to record. So what we do is we integrate train mode and predict mode with the record scope. So what's happening here is that we don't want to do this, right? We don't want to say with autograd.record with autograd.train mode every single time we train. So we have autograd.record take a named argument, right? Which is actually called train mode. And that might look a little bit funky, but basically 99% of the time for most people, that value is always going to be true. OK, so, basically the important thing to get here is that every time you call record, it's going to put you into train mode if you don't specify an argument. But there are times when you might want to turn that off. A classic time when you might want to be recording, so basically computing gradients, but you want to get the inference time behavior, is if you're not actually updating your parameters, but you want to generate an adversarial example. So if any of you know about adversarial learning, I actually want to update the inputs, and I don't want to change the model behavior. I want the production model. And then actually running it is just the same as you've always seen before. Another topic now is generative adversarial networks. We can show you, tell you a little bit about how they work and their realization in Glueon. So thus far, we've talked about supervised models. Supervised model takes some input x, generates some output y. And we basically want this output to be as close as possible to the target. So we're sort of modeling only the conditional distribution of y given x. We don't actually care when we're doing supervised learning about how is x generated, or just looking at x for its own sake. On the other hand, traditional statistics has cared a lot more about generative models of your data without necessarily framing it as sort of a conditional distribution type prediction problem. So there's some reasons why you might care about being able to get a generative model. One is that if your model tells you how likely every data point is, like how likely is that to have been part of your data set, then you can use this for things like anomaly detection. You can say, given some new observation, is that something that was exceedingly likely or exceedingly unlikely under the distribution that I observed at training time? Another thing you might want to do is you might want to actually synthesize data, something that looks like data. I don't know, maybe you're a document forger and you want to create a fake identity because you're trying to subvert the electoral process or something. I'm sure you could come up with a more useful setting, but you get the idea. This is what generative adversarial networks do is ultimately you can synthesize a face that is not actually a face, but it looks like a face based on having seen a million faces before. It's a plausible face. To get to the idea is having a generative model, actually, having a parameterized generative model, then actually sampling from it might be easy. But what's really hard is learning the parameters of a generative model. So what we're going to do with generative adversarial networks, what we do basically is the approach that's kind of innovative here, which is a really clever breakthrough by a researcher named Ian Goodfellow, is to think of, hey, we have these great discriminative models sitting around. We've seen how they could do great jobs for image classification, for image captioning, for all sorts of tasks. Could we use the power of a discriminative model to give us a good generative model? So the way you do this is basically you say, well, I have a generative model, which basically is going to be given some easy to sample from distribution. So like, I start with what we call the z vector, which is basically a random latent vector. During training, it's completely random. So I say I'm just going to sample from what's the easiest thing to sample from, either like a independent Gaussian or uniform noise. In the original paper, it was uniform noise. Now people favor the Gaussian. But basically, the idea is I can sample easily from z. Then I'm going to pass it through a neural network. And the neural network is going to give me a data point in my space. So if these are images of faces, then I'm going to pass in the noise. And what I'm going to get out is actually going to be a picture of a face. Now, the question is, how do we train that network, right? How do we actually provide training signal to it so it makes things that look like real faces? So the breakthrough here is this idea that, well, the output of the generative model, which we want to produce real images, is going to be the input to a discriminative model. So we pass noise into the generator. The generator produces something that looks like a potentially like a picture, at least has the shape of a picture. Let's say we're looking at 64 by 64 color images, right? It's going to have 64 times 64 times 3 values, and we can actually visualize it. And then we're going to pass this into a discriminative model. And the discriminative model's job is to say basically, it's going to get as input both real data and fake data. And the discriminative model wants to make, basically predict probabilistically, say what is the probability that this image is real? And so it wants to give a value that's really close to real for the actual images from your data set, and it wants to give a value that's really close to not real, right? For the fake data that was produced by the generative model. So on every single pass, essentially what you do is you're going to draw some random noise. You're going to feed it through the generator. It's going to produce a picture. You're going to feed that into the discriminator. It's going to produce a probability that these are real or not, right? And you're also going to feed the discriminator some real data that was taken from your real data set. And so you're going to update the parameters of the discriminator to say that it basically wants to say the real data is real and that the fake data is fake. But you're going to do the opposite for the generative model. You're actually going to update its parameters to make the discriminator's classification accuracy worse. So that sounds like maybe a little bit of a mouthful if you haven't encountered this concept before. If you have, then maybe it's old news. But it's kind of a clever idea here that basically we're using the fact that we have great discriminative models to provide trading signal to the generative model. You're backpropagating all the way from the discriminator's loss through the weights of the discriminator, through the output of the generator itself to update the generator's weights to induce a misclassification. So for example, if the generator is making one kind of mistake, then the discriminator will update to recognize that kind of mistake, and the generator will update to not make that kind of mistake so that it doesn't get found out by the discriminator. So, I mean, this is basically the training process right here, right? Your normal SGD loop is I'm going to iterate through my data, compute a loss, update my parameters. The GAN loop is I'm going to iterate over the data, sample from the generator, pass that into the discriminator, calculate the loss on the real and the fake data, update the parameters of the discriminator, and then I'm going to do an iteration on the generator where I'm only going to update its parameters, and I'm going to update them in the exact opposite direction. So basically, it's what we call a mini-max game. It's like a zero-sum game between the two models, and essentially, by the discriminator getting better, it's giving richer information to the generator. So let's take a look at this as a notebook. So
You probably want to run it straight from the notebook, right?
Sorry, I just followed the link. Where's your tab? Okay, I'll do the forcing out. So here's some examples that are taken from like an actual paper, like this I believe from the DC GAN paper, right, Alex? So these are actual images that they're not, real images. They're actually it's trained on a picture of bedrooms, pictures of bedrooms, I believe, or pictures of like home interiors. And through like many iterations of this kind of training process, it learns to imitate the real distribution. So Alex has created here a nice demonstration that uses sort of synthetic data to sort of show how the GAN over many iterations of training could actually learn to, for a distribution where you can actually visualize the distribution, we'll learn to match it. So here's an example of like, this is visualizing the covariance matrix of some actual real data. And we're going to define the generative model. So in this case, the generative model is going to be quite simple. It's just going to be a single dense layer. And then the discriminative model is just going to be also a very compact model. Essentially, this has two outputs for real and fake. So our loss then is just cross-entropy loss, right? So we're going to just try to get the generator to make the right classification. Get the discriminator is going to update to make the right classification. In this case, note, now we have to separately, because we've separately defined these, we separately initialize the parameters, and because we're going to want to, update the generator weights without affecting the discriminator, we're going to want to have a separate optimizer that only knows about the generator weights, and a separate optimizer that only cares about the discriminator weights. This is because we're actually going to be opposite, right? We have this value function where the generator is trying to increase it, say, and the discriminator is trying to decrease it. So when we say is trying to, this is kind of like an anthropomorphically way of saying basically we are updating its parameters in opposite directions. So the training loop, is really still quite simple. So you find it's not that much more involved than anything we've done before. Yeah?
Just makes a very naive question. There's a bootstrap problem, right? Like initially your discriminator doesn't have any like labeled samples because your data is labeled in this case.
So the labels are actually whether it's real or not. So the generator has this very complicated structured task of like output a real color image. The discriminator's task is actually just say real or not real. And so for every image, so from the very outset, we actually don't have a bootstrap problem, right? We feed in junk, we feed in random noise to the generator, feed them through junk parameters, and get junk output. But we know the label. Like we know it's from the generator. We know what comes from the generator, and we know what comes from the real data set because we actually are writing the code ourselves. That make sense? Cool. So basically here you'll just see that there's two separate gradient steps that need to get made. One is we have to update the parameters of the discriminator, and then separately we have to update the parameters of the generative model. And so what this picture shows basically from the outset, you start off with you remember the blue distribution is our sort of real distribution that we're trying to imitate. But the mapping by the generator doesn't give us anything like that. It gives us this kind of red line, which is pointing in the wrong direction and doesn't really give a whole lot of probability mass in the regions where the real data actually occupies. And over the successive courses of training, the generative model actually learns to produce something that looks quite a bit more like the real data distribution. So I think it's quite a fascinating topic, and we could probably put together a lot more slides that are specifically dedicated to generative adversarial networks, but it's not really the purpose of this tutorial. So we kind of want to give you a flavor for how to realize these things in MXNet and the sort of implementation concerns that you have. And fortunately, by having these separate sequentials and being able to grab each one's parameters separately and just instantiate two different optimizers, it makes this kind of learning process quite simple. If you're much more interested in this topic, we already have a deep convolutional generative adversarial network in the MXNet examples. So if you go to the actual source code for MXNet on GitHub, you can go to example/gluon/dcgan.py and play around with it some more, and actually train a convolutional GAN on some real data and see what it's like. But I think we're going to actually move ahead just owing to time constraints.
So one thing, and this is probably going to require a little bit of just looking at the notebook afterwards. So the reason why it's instructive is because it actually has two optimization loops really interlocked, right? So you have separate sets of gradients, and so this is to some extent an answer to the questions laid out this morning about, what do we compute gradients of, what are the variables. That's basically what this is really meant to display, besides the fact that the accounts it, right?
Yeah.
But you have to read the code. It's kind of hard to see otherwise.
Yeah, question?
Yeah, so if I'm reading this correctly, you talked before about having a list of input sets and a list of outputs. Is that using this capability here, or is this just treating it as two separate?
Let me. Where is the notebook? There we go. All right, it took only 3 hours, but with you now. So I'm sorry. You're talking about the training loop? Wait, they're still here. Data 0.
Right.
So basically, right, your iterator, we only have one real data set.
Yeah.
The other data is fabricated inside the training loop by sampling random noise and passing it through the generative model. So we only have one data iterator here. So remember that thing about having a list of inputs. This is the list of data, the list of inputs that we call batch.data. That's only a feature of the data iterator. Right? That's how the data iterator works, is it returns a list so that if we happen to have more than one, we wouldn't have to completely change the way we write our code. We would already be indexing. So that's still happening here. Any other questions? No. All right. Okay. Another topic of another kind of very popular kind of model are recurrent neural networks. The most popular of which is being the LSTM, the long short-term memory network. So here's a basic idea, and actually I think I might have the notebook handy. I think it might be easiest even to walk through.
Well, if you go to the tab to the left of it to home, then you'll see. Okay.
So far we've been looking at these settings where you have something that looks like this, right? I feed some input into the model. I calculate some hidden representations. I do this successively, and eventually I generate some output. And this describes basically just about everything that we've talked about, right? Even in the generative adversarial networks, both the discriminator and the generator have this thing. I put some input in, and I get some output out. And immediately after I do that, if I feed in another input, the neural network doesn't know. It's basically like the movie Memento or something. It doesn't remember what it did yesterday. It just knows, and it has sort of what we call like long-term knowledge that's sort of encoded in the values of the weights themselves, but it doesn't store the relationship between adjacent examples. So if I say, here's an image, and this is like from some user in Turkey who happens to be using my social network, and then here's another image from someone who's never met that person, who's like uploaded their image, and that person's in Alaska, then maybe these two things have no connection to each other, and it's perfectly fine to use a convolutional neural network because I'm passing through inputs that have no kind of semantic connection to each other. Where things break down is, say I fed an image into a convolutional neural network, and then I feed in another image, and the second image is the next frame in a video. In that case, I might actually have some better knowledge about what's going on in the second frame of the video if I remembered what the first frame was. Like there might be an object that's occluded now, but it was clear in the previous frame, and I would have some greater knowledge about what's going on in this frame if I could aggregate information across multiple time steps. Sort of the most, so we could think of it as terms of time, or we could think of this in terms of sequential structure. Like if we are trying to learn a representation of a document, we don't want to just look at each character, each word separately. We want to somehow do what humans do, which is we want to read through it one token at a time, put together some kind of representation of what we have read thus far. So this is basically what recurrent neural networks attempt to address. So here's an example of a classic task called language modeling. So language modeling, you want to basically learn a generative model for text. So one way to think of a generative model for text is basically that, say you were thinking at the character level, that basically I'm going to read in some amount of text, and then at every given point, I'm going to try to predict what character comes next, right? And given my sample of like, I say, okay, the first character is going to be T, then I'm going to predict that the next character will be I. And if I have I, then I feed it into the neural network again, then I'm going to incorporate all the information, right? So if you don't incorporate the information, you have something like this. When you predict each word, you really have no way of knowing that this M or that this E should correspond to a space. Because you don't know that, well, the previous characters were T, I, M, and so this is actually a word, and it's unlikely that someone is going to type some non-space characters after typing these four in sequence. So with a regular feed-forward neural network, you have no way to incorporate that sequential relationship. So what we want instead is something like this. we want the neural network to ingest inputs successively, but we also want it to keep track of the sequential relationships. How does each state in the neural network, its hidden state, its beliefs of what's going on now, we want them to depend both on the current input and also on its previous beliefs about what's going on in the sentence. So you could think of this almost like as when someone's talking to you. You don't necessarily memorize all the words they say to you, but you preserve some sense of the gist of it, and you keep updating the gist as you get new information. So putting this sort of in the context of the diagrams of multi-layer perceptrons is something like this. Right? Each hidden node, this is the sort of common way to build recurrent neural networks. We're going to say that each hidden node is connected not only with input coming from the layer below and outputs going to the layer above, they're also going to be connected to themselves. The hidden layer is connected to the hidden layer, but at the next time step. So when I update the hidden layer over here, I'm going to take into account the current inputs, but also its own previous values. And so this way, information from here in the very first time step at the first input can be preserved all the way to the same network at the outputs at the second time step. An important thing to note when you're looking at the network as it's depicted right here is that this is actually now that we've sort of, we call this kind of diagram an unfolding. Basically, we've drawn it, even though instead of drawing it with feedback loops that are like circles that are self-connected, we've drawn it actually sort of as a feed-forward neural network. Like there are no cycles in this graph. And this insight that any recurrent neural network can actually be drawn as acyclic sort of feed-forward neural network, just if you multiply, basically replicate it at every time step, allows you to realize that, well, we can actually then just train this whole thing by backpropagation, because it's actually, in a sense, is a feed-forward neural network. The important distinction and what makes it still a recurrent neural network, right, is that the architecture is the same at every time step, and the weights are the same at every time step. So we don't need to have an additional set of weights every single time we unfold one step. So to make this example, I actually just grabbed the Project Gutenberg, I almost said Project Ginsburg, has a freely available version of the time machine. So I just grab the time machine and say, this is going to be my training data, all the text in the time machine. So what I'm going to do is I'm going to batch it up and train a language model just completely from scratch without even using the higher level abstractions of Glueon. And this will actually kind of show off some of the advantages of the imperative approach. So the text looks something like this, right? It starts off with the title, says something about who can or can't read it, which I'm sure no one reads. It goes on. I kind of trim off some of the gratuitous legalese at the end. We're going to represent every single character numerically. So basically, we're just going to go through, grab all of the unique characters that occur in the text and assign each one a number. This allows us to we need a vector representation, right, in order to work with a neural network. The vector representation of each character is going to be what we call a one-hot vector, right? So it's just going to be if the first character is W, so it gets the index 0. And the last character is going to be C, so it gets the index 76. So capital W and capital C specifically. So, right, we can sort of map each character to its index for just really fast lookup later. And we can sort of make a completely numerical representation of the entire book. So, I mean, a few things here are a little bit hacky, but the main thing that I wanted to do is kind of give you a sense in this notebook, not of how you would actually do it using Glueon, but how you could write it yourself to actually understand what's going on, because sequential iterators can actually get kind of wild at some point. All right, so we're going to write a function that's going to turn things into one-hots. You'll see this is an example of what the second character in or the third character looks like in this document. Or sorry, the first two. The next thing I want to think about is batching. Basically what's going to happen is now every single time we feed a new input through the network, normally we just fed in an input and got out the output, and that was the end of the story. Now we're actually going to want to hold on to what was the hidden state, so that we can feed in the hidden state, because the hidden state is an input at the next time step, right? And so when you're trying to predict the H, you want to remember what was the hidden state when you were trying to predict the T. And When you feed in, same thing and so on. And so what you want to actually do is so basically you can't unfold a million steps and run all of these inputs through the network that's a million long, because you can't backpropagate across a million layers. It's become computationally unreasonable. So you're going to do something called truncated backpropagation. Basically, you're going to fix some kind of window of how far back are you going to look when you apply backpropagation. So in this case, simple case, we don't do any. There are some more sophisticated things that Alex is probably more qualified to talk about with some fancy methods for truncated backprop. But all we're going to do here is we're just going to feed it through one batch at a time. What we want to do, however, is even though we're only backpropagating across, say, like 15, 16 characters, when we start feeding in the new batch, we want to carry forward the hidden state. We want to remember what was the belief of the neural network when it was trying to predict N, and use that here when it's trying to predict E. Moreover, we want to take advantage of batching. This is where things can get kind of wacky with recurrent neural networks, is that you have these long sequences, and you want each batch that comes in to be the one that followed immediately from the one before. But you also want to not just pass through one input at a time through the neural network, because you want to take advantage of parallelization. So basically what you can do is you could chop up long chunks of strings of your text and put them side by side and then batch them up like that. So you say here, each sort of row in the batch continues sort of naturally into the row that follows it. So here's just sort of some codes to make sure the batching sort of looks more or less right, doing some sanity checking. So we can now see what does the actual update of the neural network look like, right? So before, remember, this is a feed-forward neural network. We say, I'm going to calculate a hidden layer just based on an affine function of the input. And now I'm sort of taking a nonlinear function of a linear function of the input. I think there's actually a bug that B should be inside the parenthesis. With a recurrent neural network, essentially what we're going to do is we're going to have two weight matrices in the most simple recurrent neural network, right? You want to have one matrix that is going to parameterize the relationship between the input and the hidden layer, and one that parameterizes the recurrent connections from the hidden layer to itself at the subsequent time step. So right, in this case, we have now basically one bias, but two weight matrices, so we can allocate our parameters. But you should notice that the rest of the loop actually looks quite familiar. It's quite like everything that we do with ND-array and autograd. We allocate some parameters. We're going to attach to gradients. We're still going to have softmax output, right? It's a categorical output, which is the correct next character. And finally, we're going to define the model. And the model just says h is a nonlinear function, in this case tan h, of the linear function, right, of the inputs and of the previous hidden step. We're going to calculate also our output is parameterized by a weight matrix, and we're going to take a softmax function. Use cross entropy, and basically the next thing that you need when you do any kind of language model is you need a sampler, right? At training time, your input is going to be a string, and the target is going to be the true next characters that came after each character in the input data, right? Basically your target is going to be your input, but offset by 1. So if you have hello, when you see an input h, it's trying to predict the e. When it sees now the e is trying to predict the l. When it sees the second, right, the first l is trying to predict the second l. But when you're actually given such a language model, ultimately, you don't have the true string. What you want to do is you want to sample from it. So essentially, you want to read in some prefix, which is maybe possibly blank, and then you want to predict what is the next character. And then given that character, you want to actually sample from that distribution and then feed that in. So there are different contexts when you have these sorts of language models. Sometimes you want actually the most likely string. Like if you're doing language translation, I don't care about sampling evenly necessarily from distribution if I'm trying to translate from English into French. I don't necessarily want to sample any possible translation. I might want the consensus translation of a sentence. In that case, you have a much more fancy sampler that does something that we call beam search, which is basically as you unfold, you're going to keep track of what is the most likely string so far. But in the case of the language model, we might actually want to sort of just sample plausible text. Another thing that you could do is you can set a temperature. So when you have a sampler, you could basically say, when I calculate the softmax function, I'm either going to scale all the values down, which makes them closer to each other, which makes the probabilities more uniform, or that would be setting a really high temperature to make it sort of more high temperature in the sense that it's more entropic. It's a more random distribution. Or I want to make it closer to taking the argmax, which is basically setting a low temperature. So again, right, the training loop for a recurrent neural network is quite simple. You're just going to calculate your outputs and the state instead of just calculating the outputs by passing them through the RNN. You're going to calculate your loss. You're going to call loss.backwards. You're going to update your parameters. And that's really all you have to worry about. So the LSTM is basically now just a fancier version of that. So the LSTM is basically going to say, instead of just having a hidden, fully connected layer, you're going to try to address a problem, which is that when you train really, really long recurrent neural networks that go across hundreds of time steps, what tends to happen is you just multiply against the same matrix over and over and over again, the recurrent matrix, and that tends to either squish all of your values down to 0 or blow them up to infinity and you get not a number errors. The not a number errors are actually a little bit easier to deal with. You could deal with them with a hack, which is just a gradient clipping, which Alex had mentioned before. So you just basically say, if my update is going to make my parameters move way too much, I'm either going to pass on it or I'm going to just sort of cap the amount that I can update any parameter at any iteration. The bigger problem that's harder to deal with is the vanishing gradient problem. So a guy named Sepp Hochreiter, who was a PhD student at the time, came up with this idea in 1997, which wasn't extremely popular until recently, which is the LSTM cell. So the reason, it's kind of a crappy name in some ways. I mean, now everyone knows it, so it has a certain brand appeal. But I think it confused a lot of people for a while. But basically, the intuition is this. The reason why it's called long short-term memory is that you have, in any neural network, you have basically the short-term information, which is like the activations passing through the multi-layer perceptron, say, right, which are quite ephemeral. You pass them through and they're gone. On the other hand, you have the long-term information, like actual long-term knowledge, which is stored in the model's parameters. What the long short-term memory attempts to do is essentially have like some kind of intermediate type of knowledge store that doesn't dissipate as quickly as the information passing the activations of a multi-layer perceptron, say, but it is quite a bit more short-term than the weights themselves. So the central idea to get away from this, basically, is just that you have what's called a memory cell. So the memory cell is this little box in the middle. And what it's going to do is at every single time step, its value is just going to feed back into itself, unimpeded. So in the original version, you don't even have this thing called a forget gate. But basically, the core idea is that the weight, the amount by which that self-connection has a value of 1. So just each cell's value, just at every single time step, is unchanged, but for the fact that you add to it something that is essentially a combination of the input and the input gate. So you take the current input and an input gate, which is just a sigmoid unit. So basically, it's called a gate because it says a value of 0 or 1. And you multiply them together. So it's basically, you can think of it as the cell is holding on to what it knows. The input gate is deciding whether or not you should know something, like you should add some knowledge to the cell at this current time step. And the output gate is sort of saying, should you use the knowledge inside the cell to affect the current prediction? Or should you just hold on to this information and maybe use it at a later time step? And actually, this whole model is fully differentiable. Let's see, where? Here. So here are basically the update equations, right? So you're going to have the input cell, the forget gate, and the output gate, all of which are just these sigmoid units that are calculated based on the previous state and the current input. And they're going to decide how should the cell behave at the current time step. Then you're just basically going to update the hidden cell at the current time step by adding, it's the cell that's cycled back, its previous value, zt, to this value, which is basically the input gate, like whatever has gotten past the input gate, you're going to add to the cell. And then to make the output gate, you're just going to take the value of the output gate and multiply it by the value of the cell. You happen to run it through a tan h, so there's some kind of arbitrary architecture decisions here, like why is there a tan h applied to the ZT. I mean, more or less, it's because people tried it both ways and it's tended to be more stable, or tended to blow up the other way. Implementing them in notebooks is actually, getting through to, say, a simple RNN is maybe some conceptual understanding. But from an implementation standpoint, one cool thing is that going from that to an LSTM, doing it from scratch, is maybe an 8-line code change. And going from that to an LSTM, if you're doing it with Glueon, is a 1-line code change. You're basically just changed from use RNN cell to use LSTM cell. So we talked about language models before, kind of formally. This is what's happening, right? We want the probability of a whole string. So this is just kind of expressing this in formally in probabilistic language, that we decompose this into the products of conditional probabilities. The probability of the string hello is the probability that H is the first character times the probability that E is the second character given that H is the first character times, so on. You get the idea. We sort of already discussed truncated backpropagation in the notebook, so I won't rehash it. Yeah, so, right. These are really just the key issues, right? Where you have to come up with some sequential, if you want to use RNNs, you need some sequential data. You have to figure out what are you trying to predict, In the case of RNN language model, you're trying to predict the next character. So you need some targets and know how they relate in the sequence when they should be predicted. You need some batching scheme. You need a tokenizer, right? You need some way of representing what are the individual symbols. How am I going to, in our case, we showed that through a one-hot. You need some kind of truncated backpropagation through time window, so you can actually do some learning. That's it. Another possibility, instead of using one-hot vectors, a popular approach is you use what are called embeddings. You have an encoder. I don't know if you guys, I imagine most of you have at least somewhere heard of word2vec or glove, but these are just some popular approaches that instead of giving you for every single word a one-hot descriptor, which can actually get quite cumbersome if, say, you're working with a vocabulary size of 500,000 or something. And that can happen a lot, like especially if you're dealing with online stuff where it's not so clean. You have a lot of, every single spelling mistake is a new word. And you have to decide, what am I going to do? Am I going to throw out all those new words? Or am I going to dump them all into some giant unknown word distribution? Even with just actual dictionary words, it gets unwieldy. So dealing with vocabulary sizes, like actual English and French translation, I think in the original sequence-to-sequence paper, they were dealing with things like, they had to really clip the vocabulary, and they got down to 120,000 words. And this required many weeks of training with 8 GPUs to do a reasonable job. I mean, on today's GPUs, you could do it quite a bit faster. But a different approach is, instead of having this gigantic vocabulary and always working with that, you could represent your inputs as embeddings. And the embedding is something that you might learn either as a latent factor, so you basically just you actually update the parameters of the embedding for each word, or you can learn it sort of a priori, or at least previously, you can come into it a priori, where you have learned those embeddings for a different task. It's like word2vec, for each word you try to predict the surrounding words, try to predict what is the context of the word in which it appears. It turns out this sort of easily mineable training signal of predicting adjacent words gives you a representation of words that actually is quite semantically meaningful, and you can use it to train, say, language models. Right, so we talked about sampling. That's basically the decoder. So I'd like to just maybe cap up the section by showing you what an LSTM would look like in this world. So it's taking its time. Yeah.
Actually, maybe we can do the switch.
Okay. So, okay, I apologize. This network is awful. Okay. So basically, what we already saw before is when you have an LSTM, well, basically LSTM language model, you need basically need a tokenizer, you need an encoder, you need the actual LSTM, and then you need a decoder. And the one part, by the way, that most open source language models are not so amazing in is the decoder, because that's actually real work and where a lot of engineering goes into. And that basically has to do with the fact that you may have to do a beam search rather than just sampling, a random next character, but you may actually want to look several steps ahead. So there's essentially a lot of literature on that in the speech recognition and machine translation communities. And yeah, but okay, fine. So let's assume we have a tokenizer. And okay, well, this is how easily essentially you pick different RNN cells. You can just say, well, something like, I would like to have a tang RNN with number of hidden cells, number of layers, what amount of dropout, and then, number of input dimensions. So this is fairly straightforward. This will give you, for instance, a bidirectional 4-level stacked 100-dimension input, RNN. So this is, that's how easy it is by now. And yeah, most frameworks will do that for you. The interesting part really to contemplate are those few lines here. So this is really the full language model. So you basically first take your input and you encode it. Then you apply dropout because, well, yeah, why not? We want to learn decent embeddings. Then this is the forward step of the LSTM, right? So we basically take the embedding and the hidden state, because it's an autoregressive latent variable model, and as an output, we get a new hidden state and the output, which you then would go and feed into the LSTM and take one step forward and so on, right? And then to decode things, well, that's exactly our decoder, which we can then maybe use with a logistic regression to pick the one word among 100,000 words that we might pick. Right. So this is really what you would do. This is basically just one step forward. The other thing that you need to define is basically the begin state, because, yeah, otherwise you don't know how to initialize your LSTM, right? But this is really the heart of the entire language model. There's nothing more to it. Yes, you then do a lot of clever things about tweaking parameters and so on, and how long backprop through time and so on, how you batchify things, number of tokens. So there's a lot of things. There's one more thing that I need to go through, and this is actually conceptually a new part relative to what we saw so far in terms of autograd, namely this thing called detach. You may have seen that in the GAN part, and here it's explicitly set up. So what detach does is, if you think about it, when you record autograd and so on, you look at the provenance of which variable depends on what. So you basically, implicitly, as you execute the code, you build up a computational graph. The problem is that at some point, for some variables, you actually want to cut off that dependence, right? So you basically need to cut that graph. And if you, for instance, have backpropagation through time and have a sequence of 100 symbols length, and I need to backprop through 100 symbols, that becomes ridiculously expensive. So what you basically need to do is occasionally just make a cut. And this is exactly what detach does. So detach detaches this variable from its ancestors. So this is basically where you terminate the backpropagation. And the thing that you do is you apply this exactly to that hidden variable, because as we move forward in time, we want to not look back further than, k steps for computational convenience. Not for mathematical correctness, but for computational convenience, and that's exactly what detach does. And this little function here basically takes this hidden variable and all of its descendants and everything else that's related to it and just cuts, right? That's basically this little snippet, so this is probably useful. Once you have that, everything else is fairly straightforward, and it doesn't make a lot of sense to go through it in excruciating detail here, just because we don't have enough time left for it. But I just wanted to quickly point out that little step. There is one other step that you may occasionally want to use when you look at computational graphs. So remember, when we build that graph, we say autograd record. But in some cases, you may want to do something else in between where you debug stuff and so on. You can actually pause autograd record, and then you resume. So this is in the API documentation in a bit more detail, where you can basically selectively ignore certain portions which, for instance, are there just for debugging purposes. That can make your life easier as well. Okay. So that's really all that there is to know about LSTMs themselves. And if we had a bit more time, we could later run and you would see that it does something useful. But that's what notebooks are good for. You can play with it. Now, let's attach the remote control. So there's one interesting thing that has happened from NVIDIA recently. So this has led to significant improvements in the performance for LSTMs. So essentially, if you think about it, as you have multiple LSTM cells stack on top of each other, you may want to be able to compute several LSTM cells and update them at once. Why? Because each cell is fairly cheap and tiny, right? It's maybe a couple of hundred dimensions. And if your GPU is really fast, then invoking a new CUDA kernel for every one of those operations is super wasteful. So what they've done is they've basically fused several of those updates that can be carried out at the same time together. And this basically creates this diagonal wavefront that works through your entire dependency graph as you're executing. Right. So that makes your life a lot easier. And yeah, you get that for free if you use a modern library. Now, one part that's actually quite fun is tree LSTMs, and I alluded a little bit to that before. And so okay, this is going to be a little bit equation heavy, but don't worry about the specific equations. You can look them up in the appropriate paper. So this is Tsai, Socher, and Manning, 2015. And here's what they did. So usually in an LSTM, you have one sequence of events that one depends on the other and so on. But what if you actually have something that looks more like a directed acyclic graph, where you have one variable that influences the next, that influences the next. So it's a little bit closer to actually a graphical model, really. Except that in this case they just looked at parse trees and other stuff. So in this case you have cells that have more than one ancestor. For worse and better, they named those ancestors children. Okay, well, can't help it. It wasn't me who wrote that paper. The idea, nonetheless, is quite nice. So if you think about it in LSTM, right, we have this thing where we basically have the output is some function of the current state and the hidden state, right? And then we have the cell state at time t and the hidden state at time t is some function g of the observations here, the hidden state at time minus 1 and c correspondingly, right? So this basically propagates the hidden state. This generates a new output, right? This is in a sequence. And, okay, the cleanest way that I've managed to summarize the various variants of tree LSTMs that are in this paper is essentially as follows, to say, well, rather than having a single hidden state, I now have a set of states that are essentially the ancestors of the next state. And likewise, I have a set of cells that are now the ancestors of the next cell, right? And so the different equations in that paper differ by how exactly they managed to accomplish this. And there are really two variants. One is to say, well, we have a potentially very large number of ancestors, and we don't know specifically how to treat any one of them, so basically I'm treating them all the same. Or we have a very small, let's say, 1, 2, 3 ancestors, maybe just a binary tree, and it matters whether it comes from the left or from the right, for instance. And so then you can have specific parameters for those. And, well, this is really one of the models, and I don't expect you to read even a single line out of it, except that it's a mess. And this is, even more mess. Basically, you can heavily parameterize it. Look at the details. The piece why it's relevant is actually here, right? Because now you get a model that has a variable dependency structure where essentially any individual sentence will have a very different structure over variables and so on, rather than having the same LSTM cell where it's all nice and regular. I mean, already for sentences it's a problem because they have variable lengths, but at least it's the same structure and it's just truncated at different places. But here it's actually truly different structures. And I only know at runtime, at training time or then also at test time, what the structure is. Now, if you try using a decorative framework and you basically want to parse that through, well, good luck. So hint, try searching for TensorFlow and tree LSTM, and you're not going to find a lot of implementations. But you will find a lot of implementations in Torch and PyTorch and Theano and a few other things, right? And also in MXNet, of course. And there's a notebook that goes through this in a lot of detail, which I'd love to go through, but we are running a little bit behind schedule. So we have about 45 minutes left, so I want to get to a few other things. So look at the notebook. It's a fair amount of code in there, and it'll show you exactly how to do this. It runs quickly. Okay. Yeah, and that's basically the dynamic graphs. Yeah, we already had that. So now let's talk a little bit about how to scale things. And for that, let's take a step back. So I try to summarize a little bit, brief history of computing. And I try to be correct, at least within powers of 10, in terms of, what's sort of kind of the largest data set that people looked at. Not necessarily the largest data set for deep learning, but overall the largest data sets, right? And what you can see is that nothing really happened a lot until the end of the 90s. And then all of a sudden, the data sets went up by 3 orders of magnitude every decade, right? So every time something drastic happens, I marked it up in red. Then in the 80s and 90s, memory actually went up by a lot, right? And then, so by about 2 orders of magnitude, and then not so much, and then probably, we're going to get somewhere a little bit better spot by the end of this decade. Maybe we will have, 32 gigabytes Mac laptops. Well, probably they'll be at 16, but yeah. Okay, that's a different story. CPUs, actually not so much happened, right? They went up, nicely by, a factor of 10, maybe 100. But actually something very drastic happened in 2010, and you notice it doesn't have, the x86s in there anymore, but all of a sudden it has GPUs in there. And so what really happened is, so we went up by, a factor of 100 from 2000 to 2010. And then we went up by, well, we're probably going to go up by a factor of 1,000 by 2020. Why do I think a factor of 1,000 is possible? Because by now, you can actually get GPUs. So for instance, NVIDIA Volta has 120 teraflops per chip. So I'm reasonably confident that we'll break the 200 teraflop mark by the end of the decade. Let's look at what happened actually with machine learning algorithms. I mean, this actually kind of matches it rather nicely. That we had old school neural networks for very tiny footprint problems. Then at some point when we could comparatively be wasteful in terms of main memory and the data sets weren't that monstrous, that was the time of kernel methods. Why? Because for a kernel method, you need a kernel matrix. Now, kernel matrix is something that scales quadratically in the amount of data, and that works beautifully as long as you can get away with it. And then at some point, as the data set sizes started increasing, CPU speed wasn't so great, and the memory really wasn't amazing either. That sweet spot moved. And this is why deep networks came back, right? So let's just look at how clusters look like, and we see, very, very similar setups. The main difference between, first of all, there isn't really a lot of interesting stuff happening on the networks. They go up by a factor of 10 every decade, so it's pretty lame, right? What that really means is while you get a lot of data by now, and we're going up by, 2-3 orders of magnitude in terms of data, the time it takes to move data on or off a machine takes comparatively longer and longer, right? So we are in that situation where we have the data essentially on the machines and it's stuck there, and the only thing we can really do is exchange some updates about what, aggregate I know about the data, as opposed to, how long it actually takes. So for instance, on AWS, there are, instances that have 1 terabyte of main memory, and it takes maybe about half an hour to fill that main memory from disk, if you will, right? Which is kind of crazy. The one interesting thing that has happened, though, is that the size of a cluster that you might want to use for compute has actually gone down again. So I remember running experiments on 4,000 to 5,000 machines, CPUs, in the past, and I would conjecture that by the end of this decade, we're not going to see clusters of more than maybe 100 servers with 8 or more GPUs typically. Well, this has massive implications on the type of algorithms that you use for parallelization. Why? Because if I have a small number of machines, the speed dispersion between them and all the other overheads actually go down. That makes my algorithm simpler. This is good news because it means I can use comparatively dumb algorithms and still get very good performance. If I have thousands of computers, I need to do all sorts of distributed fault tolerance and so on to get anything useful done. This is one of the reasons why a lot of the distributed computing techniques for deep learning are utterly primitive compared to what you really should be doing, right? Because you don't need to do fancy if simple is sufficient, and I'll show you a little bit what to do. Anyway, by the way, this is obviously not the whole picture. There's all sorts of things for mobile and distributed and so on. And I'm not going to go into this a lot, except that, you can export to Core ML. But a couple of interesting things really there is basically compute grows rapaciously. Data grows at Kreider's law, and that's simply the corollary of the fact that your hard disk will always be full. And if your hard disk grows at the faster exponent than your CPU, then, well, that's just what it means. Network is slow. Between compute devices, it grows quite a bit. So, for instance, NVLink is pretty good now. So the latest Voltas have 6 NVLinks at 250 or 300 gigabit. So that means memory frugal, compute intensive models are actually pretty good. So this is essentially the main reason why we are seeing now this, big surge in deep learning. Okay. Now, just a quick reminder of AWS instances. So probably some of the more useful ones for this here might be like C4s and M4s, and the C5s should be coming soon. That are going to be a bit faster. And then on the GPU side, P3 16x large. They have 16 Kepler K80 chips in there. You can go one generation more recent. That would be Maxwell's G3 16x large. So that's basically what I'm running the demo on right now. And, well, if you went to GTC, you would have seen essentially Amazon on stage as well, announcing that we'll have Volta. And the timing of that depends a little bit on when NVIDIA will be ready. So now, quick question. Who's set up a compute cluster of their own? Okay, that's actually more hands than I expected, but most of us haven't. I've done that probably more times than I would care, and it was never fun. So we did something to take away that lack of fun for everybody who has to set one up. There's something called CloudFormation template. So CloudFormation templates is basically a software-defined cluster, which you fire up using compute nodes and all of that, and we can actually quickly walk through how this works. I've set one up already, but I can quickly walk you through it. The point is, okay, don't try reading all of this. These are all the things that we basically take care of for one of those clusters, right? There's basically firewalls and security and mounted partitions and all sorts of things that you don't want to handle yourself. And this is basically a simple script, and you can git clone it and modify it to launch a cluster. Okay, so let's actually have a look at what this looks like. Okay, CloudFormation. Oh, my connection is not private. Okay, let's see whether this can be done quickly. No, I don't want to use that password. Jeez. Okay, something is very weird with the... Sorry, that demo isn't working today. Because it's... Okay, let's see. And by the way, you should always use two-factor authentication in such cases, right? No, I mean this is not a joke, because I mean treat this as carefully as your bank account, right? Because I mean, if you spend money on this, then obviously, if somebody else does it, then you're not going to have a good day, right? So CloudFormation. And so we actually started this before, and let me quickly show you what happens. Okay, EC2. So I'll show you the finished product first. So there are 5 running instances right now. There's one G3 8x large, which is what I'm using for my notebooks. And then there are 4 machines, one called master, and, well, 3 workers, which are basically a small compute cluster, and it's a G2 2x large, so these are fairly tiny machines with 2 GPUs on them each. And as you can see, there's exactly one of them that has a public IP address. That's the master. So you could SSH into this, and it will not help you if you memorize that, because, yeah, you would need the appropriate access key. But basically what it means is this is firewalled off such that there's really only one way in. And then in there, this uses the deep learning AMI, so you can use it to do distributed TensorFlow or MXNet or Caffe or whatever else training. But let's just quickly pretend that we want to create another stack. And so what you do is you git clone the CloudFormation template part that I showed you before. And okay, so we create one. And so demo KDD. I could now have some EFS file system ID. I can name it whichever way I want. And because I'm being cheap, right, let's actually use some crummy instances, C3 large. So this isn't even an up-to-date instance anymore. This is something antique. Okay, everybody should be able to log into this. That's fine. And let's say we want to have 10 workers. So that means a total of 11 machines. And so now this should actually launch fairly quickly. At some point it'll tell me that, yes, this might cost me money. Yes, okay, sure. And now we can actually see the stack creation in progress. And yeah, if we wait for a while, I mean, you actually see all the pieces that it starts firing up. It, builds queuing systems, the VPC, and the file systems, and it sets all of that up. And it's a little bit like watching paint dry, except that, yeah. So the key point is it does all of that for you, and we can maybe watch a little bit more of that later. So, yeah. Now, before we dive into more details about parallel and distributed things on MXNet, just a bit of background on why and how this all works. So you've seen the slide. This is the third time now. But let me focus on something quite important here, namely the fact that if we perform such a gradient on a mini batch, if we have multiple GPUs on multiple machines or multiple servers overall, then that means the overall mini batch actually is no longer quite so mini, right? So, for instance, we ran some experiments on 256 GPUs. Now, on 256 GPUs, with a mini batch size of 20 per GPU, your mini batch becomes all of a sudden a maxi batch of 5,120 samples per batch, right? It's quite a lot. So you need to actually adjust your learning rates appropriately to deal with that. That's just a little aside, because if you don't increase the learning rate appropriately, you get concentration of measure, and you basically spend a lot of compute on not quite that much progress. So what you really need to do is, get the data to the various compute devices, compute the gradients, aggregate them up, and then broadcast the updates. So there are really two ways of parallelizing. I mean, not only two, but these are the two extremes. You can always consider some cases in between. And one is data parallel, and that just means, well, every compute device gets some data and they all run the same model. And model parallel, which is, well, every device gets the same data but only gets to compute parts of the model. And you should not do the latter unless you're utterly forced to do so, because this creates a lot of dependency between different GPUs. So every once in a while I see papers that claim how this is really useful, but it actually is quite terrible design, because now what you have is you have those very high-speed compute devices like GPUs, and one starts generating data and all the parameters and the updates. Now you need to send this over to the next GPU, which does something with it, which sends it over to the next GPU, which does something with it. So you need very tight synchronization. You need to be very careful not to lose performance there. Can you do it? Yes, but it actually makes for fairly costly engineering. I mean, there are some examples in MXNet in the example code repository, but I would strongly advise against it unless you utterly need it. And if you need it, okay, yeah, sure, you need to do it. For instance, for very large social networks and so on, you probably need something like that. But otherwise, I would probably advise against it.
It made more sense, I think, from the original AlexNet paper.
Yeah.
They actually couldn't fit the model on one GPU. The applications were too big, so
yeah.
they needed to split it. And then even then, they only synchronized every few layers. And they had separate streams just because the overhead of synchronizing is a pain in the ass.
Yeah. So the big difference between AlexNet then and the modern computer vision networks is twofold. First of all, these GPUs now are a lot better, right? I mean, by now getting a GPU of 8 to 12 gigabytes of memory is not that big a deal anymore. At the time, 3 gigabytes was luxury. So that makes a big difference. The second thing is that AlexNet is actually pretty ugly in terms of its memory footprint. It's probably the worst possible network in terms of memory footprint of all the modern convolutional networks, right? It's this horrible memory hog at the very last end. Little piece of advice, if you ever see somebody trying to dazzle you with amazing performance on AlexNet and they don't talk about the other networks, you know that they probably have something to hide. Anyway, so just the other part about parallelization, namely synchronous versus asynchronous. And yeah, I mean, it's kind of obvious. Synchronous means, well, you do something and then you hit a barrier, and you wait until everybody hits that barrier, and then you move on to the next part and so on. And asynchronous tends to be a lot more efficient than synchronous. So you've basically probably heard of the Hogwild paper where asynchronously things are being updated. And in general, if you have more than a few hundred compute devices, asynchronous is clearly king of the hill. And you can essentially see that on the example below, where the same amount of computation is carried out in a smaller amount of time relative to the piece on top. The blue bars are exactly the same size as above and below. And you can see that, it requires less time. Now, fortunately, with GPUs, we're actually in the situation where fully synchronous data parallel works. This is a great situation. I mean, this is where we can design our algorithms in a very primitive, simple way. Well, that's good, because each individual GPU is quite powerful. So, even for 512 GPUs, you only need 32 of those 16x large machines. And, they might fit in 1 or 2 racks, so this is easy. And they have plenty of memory. And so it's a really simple pattern. So let me quickly walk you through the pattern. So let's say we have data, and this is, I'm assuming right now we have 3 machines because, well, 3 fit nicely on a slide. So data goes into the servers. This is basically 1 shard each. And so you do the usual sharding beforehand on HDFS or whatever. And then you send that data from the servers into the GPUs. Okay, so this on each GPU separately. And then, you go and happily compute the gradients. Okay, so now we have the gradients. What do we do next? Well, we somehow need to aggregate those gradients again, right? So we send them back to the servers, and the servers aggregate them, within each machine. And if you have a very good PCI Express bus, or if you have NVLink, you might actually do the aggregation within the GPUs themselves. So you might want to use something like Nickel, so NCCL from NVIDIA, as opposed to sending everything to the CPU. So that's really details. And then you push things to the parameter server. Now, this parameter server is essentially a distributed key value store. And you've heard of a lot of people talking about the parameter server. Probably one of the earliest references would be our paper from 2010 about how to do this for topic models. And the ideas have not changed a lot, except that the layout strategy is a little bit different. And actually, for deep networks, you're in pretty good shape because you don't have that many different parameter groups. Okay, and so then, once the parameter server aggregates everything, it pushes it back to the server, and that's it. So why not MapReduce? Well, right, because you could do that too, and every once in a while, people publish a paper of how they parallelize Caffe using MapReduce on some other framework. And yeah, the problem with MapReduce is that the time it takes, the overhead for map and reduce is very significant. So this can be in the order of minutes. And you're losing all the context and state in between. So the result of that is that you're spending most of your time waiting for map and reduce to complete, and your GPUs sit idle for a long time. And you don't really get a large number of iterations in. Well, Spark is a lot less bad than that, but it still has a fairly high latency. So it's really good for ETL type of operations, but it's bad for low latency updates. So if you are trying to do deep learning with Spark, use Spark for ETL for all the data transformation and processing beforehand. It's fantastic for that. This is exactly what you should use it for. Don't use it for GPUs. It doesn't even have a very nice multi-core model, let alone a model that can handle multiple GPUs in a machine cleanly. So basically, these are 2 different distributed systems, and you need to make sure they play nicely. So there are some scripts how to do that, but yeah. So how do you actually do it? Well, I already hinted at the parameter server. We really stole this idea from closed networks. This is how phone switches were designed in the 50s. So you should, go to the Bell Labs journal and unfortunately it's now behind some horrible paywall, but if you look for the paper there, you can still find a PDF. And that's basically what we did. So we basically have, the workers, the parameter servers communicating with the workers, and within each of the workers you have multiple GPUs, and it just gets synchronized to memory. So it's fairly straightforward. And yeah, that's been around for ages. Pretty much every large-scale distributed system uses parameter servers nowadays. There's a fairly detailed paper from 2014 on the parameter server. This has a lot of distributed replication tricks and so on in it. The kind of good or bad news, depending on whether you are a systems person or not, is you don't need a lot of that for distributed deep learning because the number of machines is so small. And yeah, you can do nice things with it. So that brings us to the last part, namely parallel and distributed training. And so I'll walk you through a few things. And it's on the notebooks, and then, yeah, that will probably take the next 20 minutes. And before we do that, let's have a quick look at what happened with our stack. So it's complete, and it basically, if you were to scroll through the details, you would see a lot of things being set up properly. And if I were to refresh this now, I'd see 16 different machines, demo KDD, lots of machines running. Well, basically, they're all placed in their own security groups, and load balancers, probably none here. Sorry, it would be it's in an auto-scaling group. So basically what happens is you can set the target to a specific size, and then AWS just adds the machines as they are available. There are a couple of details with GPU instances. Sometimes they're very popular, and you may not get, if you request 100 GPU instances, you may not get them. So it'll make a best effort to grab whatever is available and give you the largest possible cluster that's available with a head node and so on. Right. So this is something where if you had to do it manually, it would be kind of finicky. I'll just quickly show you how to shut it down. Actions, delete stack. Yes, so don't delete it manually, delete it through the CloudFormation template. So let's look at multiple GPUs and how we would actually train that from scratch. So if you think about it, you have a CPU, and then you have a PCI Express bus switch, and that's where you attach your GPUs. And if you have a lot of GPUs, you might have more than one PCI Express bus switch. Let's actually see what we have on this machine. NVIDIA SMI is the magic command. And let me just quickly zoom out here, because otherwise it doesn't render properly. Okay. If you were to run this on your browser and you were on a GPU instance, you would see this right now, right? So there are two GPUs, and they're sitting around fairly idle, right? No memory is really used. Okay. So then, if you look at a training loop, basically what it does is it takes the data, splits it into parts, shuffles it off to the various GPUs, they compute their grade, and you send it back, right? And you can do that automatically. But let's first have a look at what happens in terms of actually how stuff is computed on MXNet. So this is, by the way, one of the reasons why, despite this all being done in Python, you don't have to fear things like a global interpreter lock. So that basically means that Python's threading model is totally broken, but we don't care. Because what really happens is when you type in something, okay, so first of all, so here we generate a small matrix 2000 by 2000 at random, right? And we then assign y to be the inner product between x and x, right? And then in the end, I will basically convert that back into NumPy. So what happens is when I write y equals nd dot dot, and I time how long it takes, and that's basically less than a millisecond. It's about half a millisecond, right? Then all it does is it just pushes the command to the MXNet backend. And that now gets on its way and does stuff, right? And the front end immediately returns, and Python basically is almost like a terminal where you're issuing various matrix commands. And the backend ensures that you have the proper causal sequence in which you actually issue the commands that they executed to give you a logically consistent result, right? So this is why it takes about 120 milliseconds to do the computation, but it takes less than half a millisecond to actually issue it. Okay. So now let's do that on multiple GPUs. Let's just quickly run it. And basically, what you can do, first of all, is if you have things on a GPU, you actually need to copy things to that device. Right? So, and that's done simply by copy to and then context. So CTX is the device context, and you have 16 GPUs. It's from GPU 0 to GPU 15. Yeah. And so all it does is just copy stuff. Now, if I want to run things on GPU 0 and then, wait for the result and, do things on this, do the next operation, then run this, then, okay, fine. I basically, it takes some time. It takes about 0.8 seconds. Now, if I were to run these things in parallel, right? So I basically execute some code on the GPU while at the same time I'm copying something else to the CPU. Then those two operations can now actually happily execute in parallel. So it's not just computation, but it's also data transfer and computation that can happen in parallel. And you can see that one takes about 0.8 seconds and the other one takes 0.4. So the nice thing is this is all stuff that MXNet takes care of automatically. You don't have to worry. So as long as you can keep that pipeline fed with more commands to issue, you're in good shape. So now let's actually look at how you would, build a network. So this is just, some parameters that are generated. And then here's Lunet, right? So this is just, some data and just a standard updated. There's nothing particularly new in it. This is essentially very similar to what we did before.
Quick question, as you were going into some of the CUDA details, does MXNet ever run multiple CUDA kernels at the same time?
Yes. So it'll do a number of things. First of all, it will schedule multiple CUDA kernels at the same time on the device if they fit. And that's something that not every other framework can do. And at the same time, it'll actually also run, obviously, multiple kernels on multiple devices at the same time. I'm going through but the very simplest of all examples, namely the data parallel ones, because in these cases, it's very easy to explain in a demo how to reason about it. But could you do crazy layouts? Yes, you could do them, except that, well, it just wastes a little bit of time. So I would strongly advise against it because you're just going to trash the PCI Express bus bandwidth. Right? Okay, so we've done this. So here's some simple operation that simply, copies the data, all the parameters to different GPUs. Right? That's just GPU 0, copies it there, and then it's there. Okay. Now, if I want to aggregate things over two GPUs, well, it's very easy. I just have first of all, I need to actually define a number of different contexts, right? So in this case, I have 2 GPUs. I just iterate that for I in the range between 1 and 2, and then you just perform the operations and it aggregates. So this is kind of straightforward. This is probably the more interesting one, split and load, where you take the data, you break it up into segments, and now you move that data to different GPUs, right? And you do that by just calling the as in context for that corresponding segment, right? So as in context tells MXNet, move that corresponding tensor or ND array to that device. So if it's with training data, this is the quickest way of bursting everything onto the GPUs. And since this is done in parallel with computation, it's fairly easy. Okay, and so, yeah, you would see that. So this is the original data, and now it splits it up into 2 different parts. Right, it's kind of straightforward. Now, once we have that, we can just, run on a training batch. And this is basically just taking the losses, computing them for the various devices, and then you compute loss backwards, and then you just perform simple all reduce. So this is really completely straightforward. There isn't anything super fancy in it. And yeah, I could go through this now in detail here, but let me actually show you what this looks like on Glueon, because that's a little bit more interesting. Multiple GPUs with Glueon. So fine, you import GPU. Here's the network, right? This is completely standard LNet, or something that looks pretty much like LNet. Now what I do is I define a device context, namely GPU 1 and GPU 2. Right, so GPU 0 and 1. And now I need to initialize the parameters on every GPU, right? So initially, of course, the initializations will be different because every GPU does whatever it wants, right? And that doesn't really matter, right? I could explicitly write some parameters in there, but right now I don't care. So then, well, there's a simple routine that's called split and load. So this does exactly what we discussed before explicitly in code, except that here it's just one of the utilities. So I take my mini batch, right? MNIST, training data. And then what I can do is I can look at what the data on those 2 devices looks like. And of course, since we used random initialization, nothing really happens yet. Right? And so net of data, that's just because, well, we really need to, feed the network some data before it actually knows what the data set size is, what the data shape is. Okay, so since this is MNIST, we have 2 10-dimensional vectors here, because we fed 4 data points in, 2 for the first GPU, 2 for the second, right? It's the first GPU, that's happening for the second one. Okay, and so then I might go and just aggregate the weights. So this is now a specific weight. It's called CNN-conf1 weight. So the naming is automatically attached to the weights within the network by just, every layer has a name, and so it just counts, right? So this is an easy way of referencing things. Basically, this is it's a canonical way of naming the nodes in the compute graph. And yeah, it's fairly straightforward, and okay, you get some numbers and you can pull them out, and every GPU has its own. And that's kind of not so exciting. What's more interesting is we can get our hands on the gradients. So we basically take the, autograd, we compute, losses here, and then for all the losses, because we have now one per, GPU, we call backwards. This is executed in parallel, even though the code here is sequential, but remember, we have circumvented the global interpreter lock by just essentially doing nothing else but telling the runtime engine, hey, do all those things in parallel. So it happily does that. And then you can just aggregate. And yeah, that would do this quite nicely. So pulling things together, well, train batch does nothing terribly intelligent. It takes the data, like this batch, takes the device context, takes the network and whatever optimizer we have, and splits the data. So this is basically, no, I don't want to look things up in a dictionary, dear Mac. Sorry, I don't know how to disable this pesky thing. You basically split the data and the labels up. You compute gradients and do backprop, and then you update the gradients. So the code looks very similar to single GPU training, except that now we run these things distributed implicitly. Validation, the same thing here. Running, well, you can basically, after defining the GPU list, you can essentially just iterate over the data. So it's the same iterators as what we had before. You initialize your parameters and you just run. Okay, let's actually see what happens if we do this. And yeah, it basically complains that we initialize the parameters and we try to reinitialize it and it valiantly refuses to do so. That's fine. And now it takes a few seconds to run through this. Okay, and this was basically now on 2 GPUs and takes about 2.9 seconds. No, sorry, on 1 GPU it took about 2.9 seconds, and on 2 GPUs it takes 2.4. And that's quite horrible, right? It's like we have twice the amount of compute and it takes a little bit less time. So what happened? Does anybody have an idea why the result is so disappointing? Anybody? Yes? The idea might be the synchronization. Well, you're sort of kind of right. What happens is basically this is MNIST, right? MNIST has 28 by 28 bits. So in other words, we are talking about individual training observations that are less than 100 bytes in size. And we have a mini batch size of 4, which means each GPU gets 200 bytes. Right. Then, we send the gradients back and all of that, sure. But what this basically means that the work package size per GPU is way too tiny. And this is basically why the overhead kills it. I mean, it's actually surprising that we're seeing any speed up. You could be in a situation where it actually gets slower, right? So this is a little bit like, telling a group of 10 PhD students to write an abstract together, right? This will take longer than telling one of your students, right? That's the equivalent of it. So once you have larger amounts of data, you will actually see nice linear speed up, but there's just the constant overhead, and that's fairly tiny, but it exists, right? Mind you, this is 2.4 seconds for going through 60,000 observations, so it's not too horrible, but yeah. Of course, would I wish it to be, 1.5 seconds? Sure, but no, we don't. Which actually gets us to the very, very last bit, and I think we have 3 minutes left before everybody runs off for coffee. And I'm going to fake it a little bit now because of time and because it takes a bit longer to set all the machines up. So if we have multiple machines, remember the key value store, the parameter server. So what happens is basically, we have all the GPUs going into PCI Express bus switch, and then all the CPUs going into a network switch. And of course, that's not exactly how your network's laid up because you have a closed network, but whatever. So let me just quickly set up the key value store. So the key value store is really just a device where you send keys and values, right? So for a given key, you have the value. You send it there, and you can pull things back. Now, if you have more than one machine, then you can have basically a distributed key value store. And the only current ugliness is that you actually need to decide at compile time whether you want it to have a distributed key value store optimized MXNet or not. So this is one of the flags that you need to set at compile time. It's not a huge price to pay, but that's the price to pay for efficiency because this needs to be quite efficient. And then what you do is you can override essentially what put and get mean. So unlike usually in a key value store where putting a key means that now you can actually have that key, in this case it can mean that add that gradient to the values, right? Or add that gradient to the values and then do something else interesting with it. So this is basically how the key value store has been overridden. And you can, define your own override for it. And there's no way in the last 60 seconds to cover this in any semblance of detail, but this might get you started. You can run the distributed inference version of MXNet on a single machine, but it's a little bit less efficient because, of course, it tries to figure out who its peers are. And, well, it'll be very sad and say, well, I'm the only one. But for instance, if you have two machines, basically you get the servers, the workers, and you get a scheduler. So the big difference to single machine inference is that now the server and the worker, even though they sit on the same machine, have distinct memory, right? So that means if you're doing an update, you're basically sending data from one process on that machine to another process on that machine, and that causes overhead, which is basically why if you only have single machine multi-GPU training, you compile it without that. That's really the only reason. And that's it for today. I hope it was at least a little bit useful. There are around 40 notebooks in the GitHub repository, probably growing at a rate of 1 or 2 notebooks a day. Feel free to use that for teaching. Feel free to add to those notebooks. So this is essentially let's say a crazy different way of writing a book as well. So those notebooks are not just meant for teaching MXNet, but also to teach machine learning. And you just make a pull request. So this is essentially the open source equivalent of writing a book. The idea being that this way, for instance, if somebody finds a typo, they can just go and fix it and make a pull request as opposed to, dear Professor Smola, we found a comma missing on page 3 of your book. Okay, so then you update the LaTeX, and then 2 years later, MIT Press creates a new paper version of that book, and then if you didn't forget about that email from that time, that typo might be fixed, right? In about half the cases, such feedback gets lost. If you make a pull request, it's trivial to fix, right? On top of that, it's a lot easier to have co-authors and co-contributors. Right now, I think there are 12 or 14 people who've contributed to that repo so far. I mean, Zach is clearly the guy who did the most, but there's a lot of people who did that. Give it a try. You might find it useful for your students. Okay, and that's it for today. Different languages in Glueon will follow eventually, but we first want to make sure we completely nail the Python version of the interface and then find good mappings to other languages. Okay, so thanks for your attention, and that's